First of all, thanks to Senator Maria Cantwell and her staffer, Nancy Hadley, for making this room available to us today. I hope you have all had opportunity to get lunch. And the format for today is that we're going to hear from our speakers, and then, if you will, keep your questions until the end when there'll be time to answer those. So today we're honored to have Congressman Ed Perlmutter of Colorado joining us. Congressman Perlmutter represents the 7th Congressional District and is currently serving his 5th term. And so what I'd like to do first is hand over the podium to the Congressman to make some opening remarks. Thank you.
Good afternoon. I almost wore my Bronco tie, which I've been wearing for the last 2 weeks, but 2 weeks of gloating is enough. And I know we have some of the staff from the Science Committee that I serve on, and they've seen me wear this tie for a couple of weeks, and we're very proud of the Broncos. But thank you, Michael, and thanks to the panel for being here today. And this subject is very important. Obviously, it's drawn a big crowd, and you know, one of John Kennedy's rules of politics was to pick a venue slightly smaller than the crowd you expect. You guys did a very good job at that because it feels like, wow, look at this crowd. I represent the 7th Congressional District of Colorado, which incorporates the western and northern suburbs of Denver. My district and the entire Front Range, really from New Mexico up to Montana, is home to a large concentrations of federal laboratories, many private aerospace technology weather companies, and several outstanding universities, including the one I attended, the University of Colorado. Go Buffs. By working together, these entities are really able to tackle some difficult problems that have a real impact on our economy and our everyday life. So whether it's property or life, this ability to understand and anticipate the weather patterns that we are going to expect in day-to-day weather is just key. And, you know, we're very fortunate to have the National Center for Atmospheric Research in the Denver area in Boulder, and to have UCAR, which basically originated NCAR, to manage and operate that for the last 50, 60 years. So I want to thank UCAR for participating in this, and its member universities, which are, how many are there of you now? About
109.
109 universities are part of the corporation, and it brings together all of the great minds that we have on a whole variety of subjects of earth sciences and atmospheric research. And the timing of this confab today, this study session, couldn't be better. As many of you know, here in Congress, we're going to pass an FAA reauthorization bill, hopefully in the near future. I sit on the Science, Space, and Technology Committee, and we just, and I'm putting this in quotation marks, marked up a bill 2 weeks ago on the FAA's R&D programs. It was a little more contentious than any of us had anticipated, and hopefully we can move that thing forward because we really do need it from a safety as well as a research standpoint. A big chunk of that bill dealt with further research on risks related to unmanned aerial systems, which I know Joe and others will be discussing today. This is an exciting area, but new area for the FAA and for aviation, and I'm sure Joe can give us that update. But aviation is sometimes taken for granted. Millions of people fly in the U.S. every day, and we all expect the system to work. As a result, we can easily forget the research and science that goes into each and every flight. Just last week, the Wall Street Journal reported there were no fatal passenger jet crashes in 2015 due to pilot error, airplane malfunction, or bad weather. This wasn't a coincidence. It is thanks, at least in part, to the research done at NCAR, by UCAR, and all of their member institutions. You know, as someone who flies pretty much every week, I can tell you, and have been doing so for the last 10 years, over the course of that time, the bumpy flights, the flights where you just sort of drop, you know, and completely lose your lunch, have become fewer and farther between. And I actually, you know, before putting these remarks together was noticing that with each flight, it seems to be smoother and with less, turbulence of any kind. And that's because of the research that's done. A lot of times here in Congress, we get lost in, sort of the weeds of a particular bill or a particular issue that we're dealing with. But the march of science that has gone on as a result of the good work done by UCAR, NCAR, all of these universities really makes a difference in people's lives, even though over 10 years it was just like, wow, these are smoother, safer trips. And it was noted by the Wall Street Journal, no losses of life from pilot error, weather, or malfunction last year. And that's pretty incredible. I want to thank all of you for coming today. I hope you learn more about the important research and resources of UCAR and NCAR, as well as from North Dakota and our other panelists. Now, I'd like to kick this off by introducing Bruce Carmichael, the head of NCAR's Aviation Research Program. Thank you very much.
Thank you, Congressman. Appreciate very much those words. And just before Bruce gets up to speak, maybe I can just say a little bit more about UCAR and about the topic for today. So, as the Congressman already said, we are a consortium of member universities that grant advanced degrees in the atmospheric sciences, and we also run and have done for, I think, 55, 56 years, the National Center for Atmospheric Research on behalf of the National Science Foundation. And the research that is being conducted by our community helps to inform decision makers, and it also provides benefits back to society by improving our predictive and forecasting capabilities in the areas of weather, water, climate, and space weather. And several times a year, as some of you may know, we bring members from our community to the Hill to discuss the latest science in areas of importance to policymakers. And so that brings us to our briefing topic for today, when we will hear from 4 experts in the area of weather-related aviation safety, a key research focus for UCAR scientists. UCAR scientists are focusing on improved predictions of icing and turbulence. They're also working on early warnings of lightning conditions that disrupt ground operations at airports. And in addition to studying weather hazards that impact air travel, scientists are also working with unmanned aircraft systems, which can fly into dangerous weather conditions to gain valuable data about those hazards. And we are looking forward to learning even more when unmanned aircraft can fly beyond the current restrictions of visual flight rules. So, as already mentioned, Congress is contemplating the reauthorization of the Federal Aviation Authority, or FAA, and we hope there will be a strong R&D component to support safety and efficiency in our national airspace. And so, to just briefly introduce our 4 speakers, Dr. Bruce Carmichael is Director of the Aviation Applications Program at the National Center for Atmospheric Research. Dr. Carmichael is an expert in improving weather information for pilots, dispatchers, and controllers, particularly related to the hazards of thunderstorms, turbulence, icing, winter weather, and visibility. Dr. Stephen Hampton is a professor at RIDDLE Aeronautical University. Dr. Hampton is an expert in aviation issues and future trends. He was Executive Director of the FAA Center of Excellence for General Aviation from 2001 until 2013, where he led a coalition of 4 universities conducting research supporting the FAA and aviation industry. To his left, right as you're looking at it, Mr. Doug Olsen is a project scientist at the Center for Unmanned Aircraft Systems, UAS, we'll hear that acronym a few times, at the University of North Dakota. Mr. Olsen supports the FAA-designated Northern Plains UAS test site in North Dakota and leads research projects with NASA in integrating UAS safety into our airspace. Mr. Olsen is part of an FAA chartered committee working to establish UAS operational performance standards. And finally, Captain Joe Burns is Chief Executive Officer of SENSURION Aerospace in Minneapolis. SENSURION designs and builds hazard alert and unmanned aviation systems. Captain Burns is a widely recognized aviation industry expert with more than 25 years of experience in aviation technology and communications. He was the Managing Director of Flight Operations Technology and Flight Test at United Airlines, where he was responsible for more than $200 million in next-generation air transportation systems, next-gen, and technology programs. And so without more ado, I will hand over to our first speaker, Bruce.
I am just thrilled to see so many people hungry to learn about aviation weather. This is great. So I'm going to start out with a little brief history lesson. Some of you in here are not old enough to remember this, I suspect. What I want to do is talk about a problem that occurred a lot in the 1970s, the early 80s. We were losing a lot of aircraft. Whole airliners were falling out of the sky when they were taking off or landing regularly. This was becoming scary. And people didn't understand exactly what the problem was. And so this was a case where the research community was marshaled to go out and study this weather phenomena and try to understand it. And out of that came an understanding of an event called a microburst. This is the result of a microburst, and there were a lot of these. And people were getting where they were afraid to fly in an airline. So the solution, once the microburst was understood as a scientific phenomena, then what do we do about it? How do we mitigate this problem? And so the research community started working on mitigation technology. One of the first things out of the chute was something called the low-level wind shear alert system. This is a system of wind sensors, anemometers on poles, and you'll see them around airports. At Denver, we have 32 of them, 32 of these poles around the Denver airport. A lot of airports have these systems, and these diagnose the presence of a microburst inside of the network of these sensors. Another part of the solution to the problem was the development of something called the terminal Doppler weather radar. This radar now is fielded at all of the major U.S. airports that have this wind shear microburst problem. This was a joint development of the research community. NCAR and MIT Lincoln Labs were both very active in this development process and, again, deployed. And what was the result of all that? Well, the result of all of that was that the microburst wind shear problem essentially has become a non-problem in the United States. And it was a combination of things that did it. It was not just LWAS, not just the TWR. It was pilot training, wind shear training aid. A lot of things happened. Everybody focused on this safety issue, and it was solved. Well, that made us all a bit cocky, and we thought, by golly, we can fix that. We can fix about any kind of weather problem with aviation. Well, we were talking about last night at dinner the fact that, so we're very safe. Now, one of the things that we have done to be really safe is we're more careful. That is, we're more conservative in our decision-making process. And conservative means that sometimes we give up the opportunity for capacity or efficiency in the system or airspace in order to be conservative, to be safe. So the challenge now is the next generation air transportation system. The idea is that 70% of airline delays are due to weather. That's a lot of the delays. And studies show about $26 billion a year of cost because of that. And 2/3 of those, we believe, could be avoided if we were smarter about how we handled weather. So the federal government launched something called the Next Generation Air Transportation System Program, a national plan to try to renew the whole air transportation infrastructure. Now, from the weather viewpoint, we strongly believe that this program cannot be successful without vastly improved weather information. Not only that, that weather information has to be integrated into the decision support tools and processes by the airlines and the air traffic control system. So, the message here is that safety is always the controlling discipline. The problem is how to achieve safety while at the same time reducing delays, increasing capacity, improving efficiency, and oh, by the way, decreasing greenhouse gas emissions in the process. So we have to do a better job of precision forecasting with various hazards in flight, things that pilots and controllers need to understand. So let me start out and just thumb through a few of these quickly. The first one I'll talk about is in-flight icing. Now, maybe if you folks are not sort of in the middle of the aviation world, icing may not be something that you think much about. It turns out that for the general aviation community, in-flight icing is a real significant hazard. You know, we talked about 0 fatalities this year. Well, the 0 fatalities do not include general aviation. A lot of us fly small planes with a propeller that spins up in front and a few seats, single pilot operation, and not equipped to handle icing. And so there's been a lot of work funded by the FAA to try to do a better job of anticipating where that icing is going to be. We have worked with the industry, we've worked in collaboration with the universities, the FAA, and the Weather Service, and put in place technologies to vastly improve the location of that icing. But it's not a done deal yet. There's more to do. Here's another problem. This is a relatively newer problem. This is a new high-efficiency jet engine. Notice that as you look inside the engine, you begin to get ice crystals accreting on those blades. This occurs typically in the tropics, in a area downwind of a large thunderstorm, and pretty soon the engine may just stop. And this has occurred on a number of airlines. Now imagine how quiet the airplane gets for a moment when the engines stop running. So this is a major research problem. We don't have an answer for it yet, except to stay away from anything even resembling this kind of weather miles and miles away. Here's another problem. Anybody recognize the geography there? It's the New York City area. And typical day air traffic in New York City, and you see planes trying to get into New York, and there's a thunderstorm just battering the New York airports. Look at the mess of traffic. People start stacking airplanes, and they start just sort of meandering around. It looks like a random. It's not random. The controllers really know what they're doing, but it makes a huge mess and huge delays when this sort of thing happens. So research money has been spent developing a very good 0 to 8 hour thunderstorm forecasting system. It's currently being implemented by the FAA as part of NextGen. And it's been running as a prototype and providing information in the interim. And then there's another thing that thunderstorms do. Lightning on the ramp. And imagine all of those folks out there loading baggage and fueling airplanes and putting food on the airplane, and here comes a lightning strike on the ramp. It is a health and safety issue for the ramp workers, and it's also a mighty big performance problem for the air traffic control system to deal with the ramp shutdown. And everybody's going to go inside for a while and play cards until the lightning goes away. So I want to, now, I hesitated to do this, but you have to be really quick, so I'll play this loop a couple of times. If you'll watch this airplane, you're going to see lightning strike the tail, and then you're going to see a manhole cover blow off and skitter across the ramp, and you'll see people running like crazy. All right, I'll play that one again. So what happens is the lightning strikes the tail, goes through the aircraft, gets into a manhole cover right here where my pointer is, and this manhole cover goes flying off in the air. It's a big old metal thingamajig. Watch this. Whoops, sorry, let me go back. I got ahead of myself. All right, here it goes. Lightning strike, there goes the thing. There it goes. People go everywhere, right? So the question is, what can we do to not have that happen? We don't want those ramp workers out there when that's going on, but at the same time, we don't want to shut down the ramp when we don't have to. Big problem. Now here's another problem. This is a simulation, but watch, there's a drink cart in the aisle. Watch what happens. And there was a passenger, by the way, who didn't have a seatbelt on. Turbulence, a big issue for the airlines. Those of you who fly a lot, you may not have experienced this. You know, it doesn't, as was pointed out earlier, this doesn't happen a lot, but it happens. It happens often enough that people have to land airplanes prematurely and carry people off in stretchers sometimes. So we don't want this to happen. Money has been spent by the government in a collaborative way to fund R&D, to develop algorithms, to better forecast and understand where this turbulence is occurring. So algorithms have been developed and deployed with the National Weather Service, FAA-funded research. Pick a flight level, and there's the turbulence. And oh, by the way, if you do a cross-section of the flight, there's what it looks like on the vertical cross-section. Now, this kind of information is invaluable for flight planning to try to avoid these kind of situations. Now, here's another interesting turbulence event. This is a drone, a UAS, inside a hangar, wind tunnel, trying to fly with a lot of turbulence. So not only is turbulence a problem for people who fly big airplanes and medium-sized airplanes, but little tiny airplanes. And so we are working hard now to try to understand better the effect of turbulence and other weather factors on these UAS. This is an overhead picture of the Juneau, Alaska airport. Juneau is in a little bowl there, and there's a little approach down that channel called the Gastineau Channel. There were a couple or three airlines that were almost lost on departure out of Juneau because of extreme terrain-induced turbulence off of those mountains and those glaciers. So in 1997, the FAA began to fund a research effort to put in place an alerting system for the Juneau airport. After many years of work and importing technology that had been initiated at the new Hong Kong airport, a system was in place. It was turned over to the FAA for operation and now lives in Juneau, and every day runs and provides alerts for any potential terrain-induced alert hazard in Juneau. And oh, by the way, everybody will recognize that that is an iPad. What's it doing in the cockpit of an airplane? I thought you couldn't have those kind of things in airplanes. Well, this has been a great breakthrough. Suddenly, technology that you can go out and buy on the open market can now be used in the cockpit. With wireless available in the airplanes, we can put good weather information on this. And now, finally, the pilot knows as much about the weather as the guy on the ground does. It's always been an irony that the pilot is flying the airplane and is somewhat clueless, really, about the big picture and weather. The Aviation Digital Data Service, those of you who are weather geeks and like to play on the internet, go to this website. It's, if you just Google ADDS, you'll find it. It's free. It's the best weather information you can find on the internet for aviation. And this was paid for out of FAA R&D funding and then transitioned to the National Weather Service for operation. So in closing, the research community has a long history of collaboration in the aviation community, making flight safer, making flight more efficient, improving the capacity of our system. Thank you very much. And I'd like to turn it over now to Steve Hampton.
go ahead. Thank you. Good afternoon, everybody. My name is Stephen Hampton. I'm a professor of doctoral studies at Embry-Riddle in Daytona Beach, Florida. And I'm going to talk to you today a little bit about some of the safety-related weather research that is taking place at Embry-Riddle. And what I'd like to do is just to kind of march through it a little bit, talk about some of the things we've been involved in the past, some of the things we're doing now, and some of the things we'd like to be able to do in the future. So the first one we're looking at is the mobile Doppler radar imaging, which was actually a NSF-funded activity. They provided us the funding to operate a mobile Doppler radar truck, which allowed us to study the ability to perform localized radar imaging of specific convective phenomena of interest to a particular geographic zone. And the applications here include on-demand analysis of aviation operations that are currently lacking accurate radar imaging, such as remote airports, perhaps oceanic areas, and also military operations areas. Another area of interest has been the tornadic firewalls that are caused from dust devil-sized rotating columns of fire that can grow in size to a tornadic level firestorm, sometimes up to half a mile or more across. And the firewalls are really part of what a firewarders call extreme fire behavior. And large ones in particular present a significant danger both to them and also the public. While they're rare, firefighters and civilians can and have been injured or killed by these large firewalls. And some researchers believe they may be more common than has been previously thought. Research has demonstrated that the whirls can often loft debris of 1 to several meters in size, hundreds of feet in the air. So you can imagine the impact that might have on an operation where they're trying to fight the fire with aircraft, flying them low. The last item on this particular page deals with weather decision making, in particular the Women's Air Race Classic. Some of you may be familiar with, which is an annual event in which some of the country's best professional enthusiasts and collegiate pilots compete. Of course, I'm from a university, so I'm interested in the collegiate part, and I know that the UND does as well. And successful racing requires close collaboration between the race team, the flight department, and of course the meteorology department. And it allows the students to gain experience with real-world aviation weather situations and hazards, to include, at times, turbulence. Turbulence in small airplanes can be very significant, and something that people need to understand. Icing, IFR, and winds. It also, perhaps more importantly, requires the students to work together and make operational decisions as a cohesive team. Moving on, I'd like to talk a little bit about some of the current research that is taking place. One of which is of great interest is the concept of extended forecasts. Bruce talked a little bit about it earlier, about the importance of understanding what we anticipate the weather to be. Generally, airport weather forecasts are for about a 24 to 36-hour time period. That's fine until you're going to take a cross-country flight. If I'm going to fly from Daytona Beach to Denver, Colorado, it's going to take me a day or so to get there, and then when I'm there, I may not want to come back for 3 or 4 days. I need to know what that weather is going to be like for my trip back. Right now, I don't really know that. So that's an important issue. It's not only important for aviation, it's also important for the maritime industry. A couple of weeks ago, we had an issue where a cruise ship went out expecting a light chop and ended up being pretty severely damaged before making it back. Perhaps better weather forecasting and a better appreciation and understanding what that might be causing that would have alleviated some of those issues. Another area that we're particularly interested in is location-specific lighting. I don't know if anybody's here is from Florida, but Florida is also known as the lightning capital of the world. so, so we're kind of interested in lightning. And so the research attempts to determine why lightning is so concentrated in certain areas and why the strikes seem to occur primarily at night instead of during the normal thunderstorm peak in the afternoon, which in Florida is around 2:30 to 4. But a lot of the lightning actually occurs at night after the storm has abated. For example, lightning strikes on airport ramps is a high-risk hazard to ramp personnel, including, of course, refueling operations. So knowing the geographic specific inducement factors for lightning may well help produce more accurate warnings for ramp operations, increasing the level of safety. And airborne weather avoidance is something that we're very interested in. It's obviously a hot topic not only for GA, it's also one of the topics we're doing is, for example, of looking at aircraft mishaps involving ice crystal icing, primarily in the tropics. Of course, Florida's in the tropics, so at least we like to think we are. So it's pretty warm in the summer, certainly. So that's an important issue for us. Some of the needed research that we like to get involved in is looking at is working with industry to determine some collaborative research possibilities for looking at both actual airborne weather radar and comparing to simulated airborne weather radar to see whether or not we can start to use simulation to assist in avoidance of some of these issues that we've talked about, such as turbulence, lightning, and hail. Also very interested in the use of unmanned aircraft systems. I know Doug is going to talk about that a little bit later, but our fastest growing program on campus is actually unmanned aircraft systems operations. And so it's of a lot of interest to us to make sure and understand the weather that's associated with that. And also to look at unmanned systems from a point of view of how you can use them and where you can't just have ground-based systems, and certainly during emergencies such as medical evacuations, extractions, perhaps Alaskan dirt airfields, oil platform heliports, and so on. One of the things that we have started fairly recently is a PhD program, PhD in aviation. It's the first one. It's the only one in the country. It's the only first one in the world. I know that some of the other universities have started programs since we started this one up. But our students are now working on dissertations, and it's very broad, and so some of them are very interested in weather-related issues. This first one is a study of stall warning system performance during icing encounters, which we hope the candidate hopes will provide a better understanding of the interaction between the aircrew, the icing environment, and the aircraft's protection warning systems. An example of this, for instance, is the Colgan 3407 incident up in Buffalo, where an aircraft in icing stalled and led to fatalities. And so the question is, do the aircrew really understand what they were getting into as they were getting close to the stalling situation? And so we hope that this research will yield generalizable system guidelines to aircraft manufacturers, flight test personnel, and certification agencies to perhaps provide a better understanding of the issues that are involved. Another area is focuses on weather product technology development. Bruce talked about the idea of an iPad in a cockpit. Well, they are in the cockpit, and they're now portable, and people are actually able to get information pretty easily on their airborne system. And the applications that the developers have put together for tablets have benefited greatly from the popularity of multi-purpose use of the devices. And as I said, many of them are wireless and cellular and have GPS capabilities. So the study is designed to identify and understand that the role that the introduction of these products has played in GA pilot situation awareness. You know, one of the big things when you're flying is the more you understand about what's going on around you, the better you feel about it, the more comfortable you feel about it, the better you're going to be able to deal with a given situation. So we're especially interested in looking at the impact of these devices on incident and accident statistics, which to this point is truly not well understood. We spend a lot of time looking at the big-time hardware, don't look at the low-cost potential solutions that a lot of people take into the aircraft when they're going to fly. I'd like to end up with another topic which talks about centers and the idea of cross-institutional research collaboration. As universities, we think it's very, very important to be able to work with each other and have the opportunity to work with each other so we can generate the synergistic understanding and to come up with solid solutions for complex issues. Universities are unique in that they can go and pull from multidisciplinary areas. And if my university don't have a capability in one particular area, I can go to another university and pull that in. It's kind of a unique relationship, and the industry and government can take advantage of that. And so why not? And that's one of the really nice things about UCAR and NCAR. It's a collaboration, it's a center, the ability to pull universities. He talks about 109. It's a lot of really good, smart people who can get together to address an issue. And so these are two of the centers. Well, one is SENSURION, which Doug is going to talk about here in a minute, a little bit, and also Joe addressing unmanned systems. And the other one is AEROS, which is a new center, we hope, going after the FAA's air traffic organization's focus on training. They want to adjust it, get smarter about how they do their technical training. So with that, I'd like to thank you and pass it on to Doug. Thank you very much.
You just X that one off, Doug.
Oh,
X the PowerPoint.
oh, I'm in there?
Yeah, X PowerPoint. There you go.
Okay, thank you, Steve. As you heard earlier, I'm Doug Olsen. I'm with the Unmanned Aircraft Systems Center of Excellence at the University of North Dakota. And we've heard from Bruce and from Steve some of the various types of weather-related aviation research that goes on and the benefits to society and the traveling public that comes from that. I'm going to touch a little bit on that, but I'm also going to then talk about this new era that's coming on in aviation, unmanned aircraft systems, and how that's becoming a factor in this area as well. Okay, first up, I'm going to echo the comments about the collaborative nature of the work, about being able to work together across disciplines and across campuses. And one of the key things that's part of that is in some of these areas of research, you need infrastructure that can be a little bit on the expensive side, and it's not everyone can have everything. So if you can share somebody's equipment across campuses, across states, then that allows you to collaboratively work together, and not only with governments and research institutions, but also corporations as well. You see here up here a picture of our citation jet that we use for doing icing studies and wind shear studies. We've used this to go with, say, Sikorsky and other companies that are looking to certify some new equipment that they're trying to get out into the industry and through FAA regulations. So corporations do this as well. Now, other equipment we were part of the early NEXRAD studies and terminal Doppler weather radar that you heard about. And we have our own Doppler weather on top of one of our buildings there, and so we continue to do research to improve that system. And this goes to everything that you were hearing about earlier. A couple of other areas we specialize there on campus. We do some thunderstorm modeling of turbulence, so that can improve the air route planning, as we heard about. If you think it's going to be bad in this huge area, you avoid that huge area, and maybe it was only going to be bad in this one little area, and you could have not avoided such a big area. So that's some of the things that we're doing. Now, if you're going to do modeling, what does that mean? It means, you know, a lot of weather research involves computer programs where you write software to pretend like it's a thunderstorm or what have you, and then you play it in your computer and you see what the results say. Well, how do you even know how to do that? Well, you have to take a lot of physical measurements first, with called in situ measurements, with manned aircraft or with balloons or something, where you characterize the phenomena that's going on. Well, sometimes you can't do that because, I mean, would you be a manned pilot measuring high turbulence areas 200 feet from the ground? That's not a place you want to be flying yourself. But if you had an unmanned aircraft, then you could maybe go do some of that and look at some of these measurements that are hard to get otherwise. Okay, so unmanned aircraft systems. So what are we really talking about? I mean, you know, drones, right? So I mean, there's been, you know, burst on the national consciousness over the last couple of years. You know, quadcopters landing on the White House lawn is not a good thing. You know, we hear about packages being delivered to your house with these things. Is that all real? So that's kind of what people have been first hearing about this, but they've been around for a long time, 10, 15 years or longer, in the military and in the research community. And they first got their niche in what everyone's called, or at the time and still do, you know, the dull, dirty, and dangerous field, where you have a benefit that an unmanned aircraft has over a manned aircraft. So a little bit in the dull part, there's a picture in the upper right of a Northrop Grumman's Global Hawk, which is military flies, but this one's outfitted with atmospheric chemistry and all kinds of other instrumentation. Allows NASA to go out and do some really unprecedented measurements. It'll last for 20, 25 hours flying over the Arctic, the Antarctic, out in the ocean, and really get some measurements that we could not get otherwise. Moving to the bottom left there is an AEROSON by AEI Corporation. There's you know, hurricane hunters that go and fly their manned aircraft close to a hurricane, or if it's not a super strong one, maybe right over the top or even into it. But that's a little dicey, and it's important measurements, and that's why they do that. But they can't really do that at completely risky areas. But with something like this, where, you know, low cost, and you think, well, and that's what actually NOAA has done. They've flown the AeroSonde into hurricanes where they've purposely lost the bird, but they got some valuable data they could not have otherwise gotten, and really improved our understanding. So, and then in my sense, the UAS, the biggest thing is they bring to the community is as a technology change agent. Shout out to Joe, who's going to be up next from SENSURION. There's his Magpie aircraft, a little hand-launched vehicle. And you think, well, what can we do with that? Well, you can go and get these low altitude measurements that we talked of, and there's many other applications that you can use UAS for in weather-related research and other things. And I mean, there's certainly very disruptive technology, and is really turning the aviation community on its head in a lot of other areas too. Okay, now UAS in and of themselves bring a whole new area of aviation safety challenges, not weather related. So on the picture on the left is a chart from NASA. It's a bit of an eye chart, so I'll just try to walk you through it. In the center is this Icona, it's the name of it, research aircraft, and it's what's being depicted here is that when you have an aircraft up there and the pilot on the ground, you have to maintain a link to it, a radio link, so you can control it. And there's a couple options shown up to the satellite and down, or straight down to the radio link. And you also need to talk to the air traffic control, and then you have to avoid other aircraft. And there's really two kinds: the cooperative aircraft, the kind with transponders on it that electronically say, here I am, and your bird can see them, and vice versa, electronically anyway. But then there's uncooperative aircraft, and those are the hard ones. You know, you have a general aviation aircraft out there that doesn't have an electronic transponder, and you can't see them very that way. So what's shown on there is like an air-to-air radar that's sweeping out there and trying to replace the pilot's eyes. So that's a huge research area, and the holy grail for unmanned aircraft is what's known as beyond visual line of sight, or BV loss. You know, the small aircraft UAS rule that a lot of people might be familiar with is all about flying only a few hundred feet away, always within visual line of sight of the operator, And that's great for a lot of initial small commercial things. But to try to get something fly many miles away from you is what BVLOS is all about. And the folks doing that are shown up there, NASA, FAA, and industry trade groups like RTCA. But what's needed, and what we're talking about in this forum, is using unmanned aircraft for weather-related safety research. And that's what I'm using the term beyond VFR. VFR is a pilot term. You either fly under visual flight rules, or if you're more skilled and you can fly by instruments, that's under instrument flight rules. And right now, the small aircraft rule, you have to have good weather. And there's a lot of unmanned aircraft systems that just can't handle weather, so they fly in only good conditions. But the next step for this community is to be able to send unmanned aircraft into a nice little prairie storm like that and take some good measurements and see what we can learn. So what's a good way to do that? Well, there's a lot of initiatives at the FAA that are going forward with unmanned aircraft systems. Some of you, I'm sure, most of you are familiar with that. The FAA designated 6 test sites around the nation 2 years ago. In North Dakota, we have the Northern Plains UAS test site. Right here, we have the Mid-Atlantic test site, and there's 4 others listed around the country. Now, these test sites were picked for their safety record and their capabilities, but also for their diversity. That was one of the key factors. And so if you think about the states that are listed, they are in vastly different meteorological situations and can investigate weather under many different scenarios. This is a depiction of operations at our test site, but I'm sure it's similar to everyone else. To do this safely, you have all these visual observers on the ground, spotting aircraft to make sure you're safe from the other aircraft. You need a ground control station and missions control center and radars, but most importantly, safety and skilled people to do it right. And so that's what's been stood up, and these test sites are serving the aviation research community. They're serving the UAS industry partners as well as all of the end users. And that's the key point about UAS and aviation, is that the end users of UAS are vastly different than the end users of the transport industry. Transport is getting people one place to the other, flying on United or all the other airlines. Well, here the end users are farmers, agriculture, research. You have pipelines, you have power lines, you have railroads, you have things that need monitoring, and so that's a whole different set of end users. Okay, to kind of wrap this all up then, I guess my main takeaway point is there's this existing infrastructure through UCAR, NCAR, all the member universities and government agencies that have this capability to do weather-related research for aviation safety and for other reasons. But if you marry that up with some of the new capabilities coming out of the FAA, the test sites I talked about, and what's recently been set up is the Unmanned Aircraft Systems Center of Excellence, and that's SENSURION. That Steve mentioned earlier. There's 22 research universities and a host of corporations that are part of this project, and we're going to be moving forward with FAA to do research into safely integrating the UAS into the national airspace. And those two together will give us a whole new era of aviation safety that we can rely upon. And just a couple of closing thoughts on these pictures. You see the one on the left, we've all been there sitting on the tarmac, with rain coming down, you're looking out the window, and most people don't give a second thought about whether that's safe to take off, because trust the system, and they're going to be, of course they are going to be safe. Well, the picture in the middle is an MQ-9 being flown by Customs and Border Protection out of the Grand Forks Air Force Base in North Dakota. It's a nice sunny day there, right? Well, it's because you don't see too many pictures of drones flying in weather, because they are less able to do that. And research can really improve the mission of Homeland Security and the Defense Department as well. And then on the right, the emerging economic applications of UAS. There's a drone looking at a pipeline and looking for leaks. Well, pipelines don't necessarily break only on a nice day. So all weather capability would be nice to be having there. So weather-related research is important for the transport industry, as we've heard, but for also all the future applications that unmanned aircraft systems are going to have. And with that, I'll introduce Joe Burns from SENSURION. There you go.
Thank you. All right, Bruce, where's the wrong one? Hey, I'm the tech guy too, so,
It's just like flying a 747.
yeah. With every subsequent version of PowerPoint, it seems to get harder for me, so maybe I'm just getting older. Thank you for coming today. I appreciate it. My name's Joe Burns. I'm a former airline guy. I've flown everything from wide bodies to drones. So, and I'm happy to say I'm probably the highest time drone pilot who's actually flown wide bodies. So that's something to talk about at least. Remember Bruce's deal, wear your seatbelts. If you take anything away from this, we'll take a couple things away, but one is wear your seatbelts. It's always a good idea. We're going to talk about weather safety and how it impacts all aircraft. They all share the same airspace, and they have a couple common things, right? We have to fly under the same rules, and we have to follow the same airspace. So it's important that we have a capability, on the other hand, of weather input into the system. And I'm going to talk about it from small up to large. So the first thing I'll talk about is unmanned systems, just to give you a little familiarity, but a couple of typical UAS types. These just happen to be ones that we manufacture, but the fixed wing, very conventional looking aircraft, does a lot of the same missions, can stay in the air from 1 to 2 hours, can carry a tremendous amount of sensors. In fact, so many things we can do that one of my investors has told me we're on the 1 yard line with 99 yards left to go, and that is because of all the applications. You know, right now you hear about cameras, great pictures, a lot of fun, get some good stuff there, but there's so much more we can do. So we're able to carry environmental sensors, weather sensors, you name it. It's security applications. There's a tremendous amount. But these aircraft fly anywhere from 0 to 60 knots, say about 68 miles an hour. Typically cruise around about 20 miles an hour. So you have a lot of hang time up there, a lot of good opportunity to view whatever you want to on the ground. But what's most amazing about these is this technology is really not new. What's new is the miniaturization and the ability to put a full suite of regular avionics or aviation electronics in this aircraft. Now the sizes are just staggeringly small, and if anybody wants to see afterwards, I've got some samples of that. But it's unbelievable what we can do now with a small aircraft and have the same computer or even more processing capability as you do in a lot of large airplanes. On the right-hand side, it's a multi-rotor. You've seen quadcopters, octocopters, all those. Ours happens to be shrouded for a variety of reasons. But they're easy to fly, right? But they don't stay in the air very long, 20, 30 minutes probably. It can do about 20 knots of speed forward. So much so that number's important. Why weather's important is if you have a 20-knot wind and you can only fly 20 knots ahead, guess what? You're going to be chasing that thing downstream somewhere. So it's really important that you understand what the environment is like before you go off and do a mission. Real strong reliance on GPS, real critical component of ours. And 90% of the vehicles out there doing commercial work are this. Probably 98% of the toys out there, or the ones that everybody got under the Christmas tree this year, are kind of the multi-rotor design. But aviation weather is critical to these as well. And there are now, something like 400,000 of them estimated in the United States. But very little attention has been put on all the supporting features and the ability to get weather and do the things like that you need to do to fly them safely and integrate them into the system. The weather access is important, as I just mentioned. We're working with UCAR, NCAR, to specifically develop applications for the unmanned systems. And it's important that that operator be able to go to an iPhone-like of an application, pull up the app, get the weather, get the airspace restrictions, do all these things so you're flying legally and safe. And that's something that we're working on. I think it's really kind of critical that the user has that access. Without the easy access, it'll be a long time before people actually get out and actually do the stuff that they should be doing as proper aviators. But in addition to all this sensor information and stuff up to the aircraft, as I mentioned before, we can carry a lot of sensors on these things. Typically, the middle picture there, the balloon, those go up twice a day. We get great atmospheric information from them, radiosondes. But again, it's twice a day. It's not as granular as we'd like it to be. Far right, of course, is the typical AWOS type of an installation where you have that continuous information. Again, it's looking for weather on the ground, and we have a lot of weather in the atmosphere above us. So a couple new developments, that kind of chrome probe thing in the middle is known as a TAMDAR sensor. And that's one example of being able to fly around the air on an aircraft and turn the aircraft into a flying weather station. So we're now getting much, much better information back to the ground. The other, of course, is using a UAS. And if we start equipping UASs with these sensors and send the information back to the ground, the quality of the forecast will be staggering. So we send that information down, we process it, send it back out. The societal benefits will be staggering because there's so much that we can do now with that low altitude weather combined with the high altitude, put it all together, and we've really got a phenomenal thing. I'm sure forecasts will get more accurate. You know, that picnic forecast for tomorrow, those types of things are all societal things that people really won't know what's happening, but the reality is with thousands of sensors in the air simultaneously, the granularity and the accuracy gets much better. You can also use unmanned systems, and we've actually got this up and running for plume modeling. So if you want to know if something's happened, whether it's nefarious or just an accident, and we all read daily, it seems like that there's some kind of a car that overturns, it's carrying some kind of a liquid, you've got to evacuate the area. Now with going up a little bit, flying around and getting a real accurate check on the weather and the conditions, temperature, humidity, wind direction, we can calculate almost instantaneously a plume and a dispersal model, so we know where all the bad stuff's going to be going, and more importantly, who to evacuate and get them out of the area, or if there's even a hazard. So those are all the things that we can start to do with unmanned systems that have already been proven and are ready to go out and fly. If we talk a little bit about general aviation, you know, the FAA talks about their goal of 10% accident reduction over the next 10 years. I think we can do much better than that. 3 of the top 10 are directly related to weather. All the others have some component of weather. But with that information now, a lot of it is a lack of information to the crews and to the pilots of these smaller aircraft, the ability to send through a program that you're probably familiar with called ADSB. Terrible acronym, by the way, but nonetheless, that is the system that's up and running. We have the ability to send weather real time to aircraft. And putting that weather on displays now, lots of companies are doing. There's Aspen Avionics on the left. There's some systems in the middle, and on the right-hand side, just using a standard iPad and getting the information up to it. But now that the user has this big picture, so to speak, and there's just such a tremendous safety benefit to that. It's happening today, and it's all thanks to efforts that have happened on the Hill and funding and things that have done to make this a reality. So I think we'll start to see a fairly significant accident rate reduction due to weather on the general aviation side because of these tools, and people are really learning how to use them. On the airline side, there's been a lot of work done. This happens to be one that I was involved with back in my old company, but Bruce kind of mentioned this, but it's something we did with NCAR directly, and it's the ability to send a graphical turbulence weather to the flight deck. And if you think about it, you're flying along 31,000 feet, and you start to hit bumps. The first thing the captain's going to get on the PA and say is, we're going to climb up and try to find a smoother ride. Hey, that's great. You can climb up and get a smoother ride, but you're kind of basing it on what we call the coconut net. So you're hearing other pilots talk about it, and you're asking air traffic control where the rides are. To have a real graphical picture of that information in the flight deck on what's called a EFB, electronic flight bag, which is now available in just about every airliner due to iPads and Surfaces and so forth. We have the ability now to see that graphically and have that information. Now you can slide in your altitude and say, hey, it looks like flight level 330 or 33,000 feet looks better. Let's climb up there. But more importantly is when you're past that weather event, it's rare that you would be prompted to come back down to your original altitude. That altitude was picked for a reason, whether it was because of other turbulence or weather factors or wind direction. But now you can kind of go back and optimize your route. So there's a huge societal positive impact on that. The blue trails there, the mouse trails, so to speak, those are from other aircraft that are actually reporting real-time weather back into the system. And they're flying around every day due to the MedCar system in reporting the weather and ride conditions back to the ground. Another project that I'd worked with in the past with NCAR is something called OCND, Oceanic Convective Nowcasting. And if you think about it, a lot of water out there. You get out over the ocean, you don't have the weather radar other than the airborne radar on the aircraft, which is phenomenal, but it's only good out to about 15 minutes of flight time. So you're making tactical decisions. When a long track, strategic decisions, if you're out over the Pacific Ocean for 10 hours, it's nice to have that long-term information. So you can send that now to the aircraft, and we've actually demonstrated this on multiple flights. Started out with a kind of a graphical printer that's known as the AEROSPACE system, and have worked our way into a full iPad type of display. But if you think about some of the more infamous incidents and so forth that have happened over oceanic areas, having this ability to see that weather and really make some flight decisions around it is really invaluable. And this is available today with the technology that we have. And the last slide talks about convective weather reroutes. And if you think about it, you sit on the ground and all of a sudden you'll hear the captain come back and say, hey, we've got to it's going to take us a little bit of time. We've got to reroute due to weather en route. And in this particular case, it was one that our crews were on, but the flight plan was from Denver to Philadelphia. That's that purple or magenta line on the top. They came back with the green line on the bottom. So it's a pretty significant reroute. And the reason is the weather changes so much without having that real-time weather in the flight deck. Now you've got this big gap. You want to just be super cautious, but because you don't have the information. But now with having this information on an electronic flight bag, you can now look at it and make proactive decisions. So much so proactive that the crew is actually able to make dynamic or reroutes and get closer back to the original course and actually save 25 minutes of flight time and like 2,000 pounds of fuel. So the technology is available. This is something that's happening today, and it makes a huge difference as to how we fly and operate aircraft, and really makes the system a little bit smoother. So a couple of takeaways. Number one, wear your seat belts. And number two, help us continue the good work of this aviation weather activity. It really does work. The benefits are staggering. There are huge numbers of delays out there that are caused by weather that may not even be there because we don't have enough information to fill in the gaps to see how conservative we really are. So if we can continue down this path, it's just going to make those flights smoother and smoother, as the Congressman said a little bit earlier. Thank you very much.
So thank you, Joe, and thank you to all of our speakers. Now it's your turn. We have 10 or 15 minutes for questions. Yes, please.
Randy Bass from the FAA's Aviation Weather Division, actually the Convective Weather Research Program Manager. So I help fund Bruce and several of his folks. But I got several comments I wanted to make. First of all, thank you very much for putting this on. I think it was thanks very much for putting this on. It was very informative. And we can use all the publicity we can get. I want to make a couple of comments. The 70% flight delays, that's about a 7 or 8 year old number. I've looked at it the last couple of years. It's running about 53% now. That's a good news story, and it's because of the aviation weather work that's been done by UCAR and others. That's probably not all of it. A lot of what we do doesn't matter if it's not translated into operational decisions. And I think we've done a better job of getting controllers to make better decisions based on that weather information. So, but again, that's, it's an end-to-end thing. We do a pretty good job CONUS-wide, Alaska and overseas and offshore, especially the transoceanic flights. We still have a lot of work to do, and Joe just mentioned that. But that's an area we still need to work on. Weather technology in the cockpit. There's some great things going on out there, but there's a lot of issues there too. Right now, it's, especially on the iPad side, it's very unregulated. A pilot, especially a GA pilot, can pull any information he wants off of there. Doesn't mean that it's correct, doesn't mean that it's right, doesn't mean that it's timely. So we've got a group called Weather Technology in the Cockpit, which probably isn't a good term for it, but it's a group at the FAA that's working not necessarily to mandate, things, but at least to present some guidelines. A perfect example of that is a couple of years ago we had a GA flight that flew into a thunderstorm because they were looking at their iPad at the radar, but the radar was about 10 or 15 minutes old. And that's some of the issues that we're trying to work out. And the last thing I wanted to mention was just remember that most of the work that we do on the aviation side has applicability to many other areas. We do a lot of work with improving the weather models themselves for aviation, but that translates just into a better forecast for the general public as well. So again, thank you guys, and appreciate the opportunity.
Thank you, Randy, and thanks for your partnership and support.
Hi, I just wanted to ask about research to operations, because a lot of what you've talked about today demonstrates the translation of research into operations, and what you think helps make that process successful?
I could take a quick stab at that. One thing is to getting cooperation of the various, whether it's an airline, it's a particular corporate jet operator, or a GA group. And there's been a lot of success in the past of kind of working up those projects and getting the right teams. I know for one, my old carrier, we were very active in this participation. All the other carriers are as well. In fact, there's always someone to raise their hand and say, I want to help do a test or an experimental scenario. Take airplanes out of service and fly things. So there's a tremendous amount of desire within the aviation community to do that. I think you're going to see the same thing on the unmanned side as well, where companies are going to say, here's an aircraft, let's go try this out. And in fact, that's happening every day today because everything is so new. So it's working, and that's the best way to translate a research project into real reality.
So let me take a different stab at it. A partnership between the FAA and NOAA, the National Weather Service, I believe proves to be one of the most useful research to operations mechanisms that we have. As you know, the Weather Service is responsible for providing aviation forecasts. The FAA is responsible for doing aviation weather research. So there's a partnership there that's just sort of built into the way the world is set up. FAA does the R&D. They work with the Weather Service and NOAA and hand it off, and NOAA operationalizes it. So that, I think, has been one of the most helpful kind of mechanisms we've had. For example, the Aviation Digital Data Service, developed by the FAA, implemented at NOAA, the graphical turbulence guidance, the current icing potential and current icing forecast, the National Ceiling Visibility product. There are just a whole number of those things where the FAA has been able to do the R&D, but has not had to do an acquisition program in order to make these things operational.
And I'll just do a quick add to that in terms of getting operational. In the aviation world, it's heavily regulated for safety and for very good reasons. And the regulator needs to be able to get to the point where they feel comfortable that this has been well vetted. And to get that, if you have new technology that's coming in, it needs to be demonstrated, needs to be tested. They're not going to just one day turn the switch and suddenly do something that hasn't actually been proven to them and to others that it works. So you need that demonstration period to get the regulators to agree and make the change.
Thanks. I think we have a question here, and then there's one at the back, and then one right here.
Yes, Mike Farrer, National Weather Service. Traditionally, over the last several decades, weather forecasts have been provided in a deterministic sense. You have icing here at this time and place, or you don't. Now, with the advent of a ensemble modeling and greater supercomputing, we have the much better ability to provide probabilistic type information, where you have a spectrum of probabilities of an event at a time and place. A lot more information contained there, but it's not something that humans typically assimilate. And I know that that dynamic routing example that was shown where you fly around the thunderstorms, that kind of capability could really easily automated consume probabilistic information. What about the nascent UAS consumers as well as general aviation? Where do you feel that in the spectrum of their ability to consume weather information, is there a growing demand for probabilistic information? And if so, how do you think that should be delivered as it becomes available?
Yeah, good question. It's to date, UAS operations for commercial side are largely limited to line of sight. So you kind of look up, and if you know what the winds are and you've gotten a basic weather forecast, you kind of know what it is, right? So it's not a huge need today, but as soon as we start the beyond line of sight where that unmanned system is over the horizon, flying something, it's critical because it's just like an IFR operation. So I think you're going to see in the very near future a real demand for that information.
And better, thank you.
Question at the back.
Yeah, one of you mentioned TAMDAR, and I was just wondering if you could touch on sort of the progress with the in situ measurements and where the industry is with that kind of equipment or similar type of equipment. Is that being talked about being put on commercial aircraft? And I don't know if you know anything on that subject.
Joe?
Yeah, I'll touch on that only because I was one of the original inventors of this system, but I haven't kept up as much with where they're at today with the commercial side. I know it's been deployed on quite a few airliners. And the other side, there are other sensor systems out there too. MedCars is one that we mentioned a little earlier, and that's the ability to take the aircraft information that's already on the aircraft and transmit it out through the AEROSPACE system. So we certainly would like to see more and more aircraft doing that. I know it gets expanded all the time. I just don't have any exact numbers to provide for you.
So on the ACAR side, right now, United Airlines, Delta, and Southwest are all heavily equipped and downlinking the in situ information, and that information is actively being used as part of the forecasting process. We still have a ways to go in terms of the airlines sharing this data directly with each other, but I think that will come.
And a question right here.
One of the kind of hottest topics in this FAA reauth is the idea of spinning off the ATO in the ways that other civil aviation authorities have done across the country or across the world. And I just want to get the panel's thoughts on whether or not you see that would be helpful or harmful based upon other kind of international models, you know, particularly the one that's being discussed is a lot with NAV Canada, and where you saw that. Was that particularly helpful to have the air traffic managers be in a separate organization from the regulator, or is it most helpful to have them housed within the same kind of governmental organization?
So
I guess I
don't know if
trying
Joe
to
wants
dance
to.
around this one, but you're going to get an answer from them too. You know, I'm very familiar with the NAV Canada model. I think it's worked very well up there, and the critical part of that is that you, no matter what you do, whether you separate it or not, I guess I'm ambivalent to personally. But the reality is you have to maintain the safety and oversight functions somewhere within the federal agency. So as long as that's done, it's done today very well, and I think that'll continue no matter what. Then I think it could be success if they implemented it, and you know we're going to be a success moving forward no matter how we do it.
And thank you. That's a very excellent question. And then I let me officially punt since it's not my area of expertise. So I really can't say anything with respect to unmanned aircraft systems. Though that that is a disruptive technology, and that's coming in to the system, and that's going to start affecting the air traffic control operations as well once they become more and more mature. So whichever model is used, keep it in, move it out. I'm agnostic. I don't know anything about the pros and cons there, but either way, it has to adapt to new technology and continue to do that well.
Yeah, I would also perhaps add that it's not just a matter of adapting to the technology and the changing technology. You also have tremendous growth. And if you think about the number of UAS systems, if they get to the point where they're actually in the natural airspace, then you've got a huge workload issue, right? So whatever system you develop, you've got to be able to accommodate it and adapt to that change rapidly, which is I think one of the greatest challenges.
So let me just put one footnote on this, and that is, I think from my standpoint, the issue that's important is a stable and predictable funding stream over multi-year programs. And without that, I don't think we can hope to be successful in the next gen effort.
Okay, on that note, with my eye on the clock, I think we will draw the formal proceedings to a close. So, as we've heard today from our four experts, while aviation safety has become safer, continuing to improve our prediction of weather hazards is important for keeping our skies safe in the future. So I'd like to thank our speakers, and to all of you, thanks for attending today. If you would like, please reach out to our speakers or UCAR staff in the room if we can answer more of your questions. Our next briefing, which I believe will be in June, will be on the subject of space weather. So thank you all very much.